Welcome to our Quantum Deep Dive.
Great to be here.
Today, we're tackling something pretty cutting edge, quantum accelerated backpropagation. It's potentially a whole new way to train AI.
That's right. And we're drawing heavily from the essay Quantum Accelerated Backpropagation, KI New Defined, by Yorgo Schneeppot. It gives a really good overview.
Yeah, it does. And look, if you want to stay informed, understanding how quantum computing might, break through the current limits of AI training is becoming super important. Classical methods are hitting a wall.
Definitely. So our mission today really is to get our heads around how this quantum boost could actually work. How could it make AI training faster, maybe more efficient?
Okay, so before we jumped into the quantum side, maybe we should quickly recap the classical way, backpropagation.
Good idea. So classical backpropagation, it's really the workhorse algorithm for training most neural networks today.
Right. It's how the network learns from its mistakes, basically. It adjusts its internal connections, its weights.
Exactly. Like tuning an instrument. It figures out how much to adjust each connection based on the error it made in its prediction.
And this relies on calculus, right? Gradient descent and the chain rule.
Precisely. Gradient descent is like, imagine you're on a foggy hill and want to get to the bottom.
Yeah.
You feel the slope around you, the gradient, and take a step in the steepest downward direction.
Okay.
And the chain rule is the math tool that lets the network figure out how changing one tiny connection way back in the early layers actually impacts the final error, even through many, many layers.
Got it. So what's the problem? Why look for a quantum alternative?
Well, the essay points out a few big things. First, just the sheer computational cost.
Yeah.
Modern AI models have millions, sometimes billions, of these connections, these parameters.
Yeah, training something like GPT takes forever and costs a fortune.
Exactly. It's incredibly time-consuming and energy-hungry. You need massive computing power.
Okay, so cost is one. Anything else?
Another big one is the vanishing gradient problem, especially in really deep networks.
Ah, I've heard of that. The error signal gets weaker and weaker as it goes back.
Yeah, precisely, like a whisper getting lost down a long hallway. By the time the signal reaches the early layers, it might be so faint they barely learn anything. It hinders optimization.
So we need something better, or at least different, for these huge, deep models.
That's the motivation. And that's where the essay suggests quantum computing might, just might, offer a way forward.
Okay, quantum computing. Let's dive in. How can, harnessing quantum mechanics help here?
The potential comes from these really non-intuitive quantum principles. The essay mentions superposition.
Right, where a quantum bit, a qubit, can be both 0 and 1 at the same time, unlike our regular bits.
Exactly. And entanglement, this spooky connection where qubits are linked,
Yeah.
and measuring one instantly tells you something about the other, no matter the distance.
Weird, but powerful.
Potentially, yes. These properties allow quantum computers to explore a vast number of possibilities simultaneously. It's a fundamentally different way of processing information.
So instead of step by step, it's like massive parallel processing.
That's a good way to think about it. It could offer, potentially exponential speedups for certain kinds of calculations, and calculating gradients might be one of them.
Okay, but quantum computers today aren't perfect, right? They're noisy, limited qubits.
Absolutely. The essay is clear on this. We're not running full AI training on quantum computers yet. It's just not feasible.
So what's the approach then?
Hybrid systems.
Yeah.
That's the key idea in quantum machine learning, or QML right now. You combine classical computers with quantum processors.
A tag team effort.
You got it. The idea is to use the classical machine for what it's good at, managing data, overall control, and then offload the really tough computational bits to the quantum processor.
Like calculating those gradients we talked about.
Exactly. That's often the bottleneck. So if a quantum processor could do that part much faster, you'd get a significant overall speed up.
Makes sense. The essay mentions some specific ways these hybrid systems work, like VQCs.
Yes, variational quantum circuits. Think of them as small quantum programs with adjustable knobs or parameters. A classical computer tunes these knobs to minimize some cost function, often related to the AI task.
So the classical computer guides the quantum circuit?
Kinda, yeah. And then there are quantum kernel methods. These use quantum effects like superposition to help measure how similar data points are, even in incredibly complex spaces. That's often hard for classical machines.
And there are specific quantum algorithms that fit into this.
Yeah, the essay mentions a few. Grover's algorithm, which is famous for speeding up search that can be useful in optimization parts of AI.
Okay.
The VQCs themselves are a type of algorithm, and QAOA, the quantum approximate optimization algorithm, is specifically designed for finding optimal solutions, which is core to training.
Right, so let's zoom in on the main topic, quantum accelerated backpropagation. The essay really stresses how much compute power current AI needs. How does quantum aim to tackle the backpropagation calculation specifically?
The central idea, as laid out in the essay, is to use a quantum system to directly compute the gradients.
Instead of the classical step-by-step chain rule thing.
Exactly. You design a quantum circuit that encodes the network's parameters and somehow the gradients themselves within the quantum state specifically, in the amplitudes, the probabilities of measuring certain outcomes.
So the answer, the gradient, is kind of embedded in the quantum fuzziness.
In a way, yes. And because of superposition, the quantum computer could potentially calculate gradients for many parameters all at once, in parallel.
Okay. The essay gives a simplified picture, right? Encoding then, a quantum Fourier transform.
Yes, the QFT. It's a quantum version of a standard signal processing tool. The key thing is, it lets you analyze the frequencies within the quantum state.
And those frequencies tell you about the derivatives, the gradients.
That's the core insight. It relates the structure of the quantum state to the rates of change you need. So you encode the problem, run the QFT, and then measure the qubits.
And measuring gives you the gradient values.
It gives you information to estimate the gradient values, which you then feed back into the classical part of the training loop to update the network.
Wow. If that works at scale, the advantages seem huge. Speed, obviously.
Speed is the big one, yeah. Potential for exponential speed up in that gradient calculation step. That could slash training times.
And maybe energy efficiency, too. Less computation overall.
Potentially. Fewer computational steps might mean less energy per training run, though current quantum hardware has its own energy demands, of course.
Right. And the essay mentions accuracy. Could it be more precise?
There's some thought that for very complex optimization landscapes, quantum approaches might navigate them more effectively, possibly finding better solutions than classical gradient descent, which can get stuck.
Okay, let's touch on the math briefly. The essay contrasts the classical formula with this quantum amplitude encoding.
Right. Classically, you have an explicit formula for the gradient, while quantumly, it's more about preparing a state where the amplitudes represent the gradient information.
And the QFT formula. It looks complex, but its job is just extracting that frequency info.
Essentially, yes. It transforms the state into a basis where the frequencies, related to derivatives, become more apparent upon measurement.
And amplitude amplification, another quantum trick mentioned.
Yeah, that's related to Grover's algorithm. It's a technique to boost the probability of measuring the specific quantum states that hold the gradient information you actually care about. Makes the measurement more likely to give you the useful answer.
Like turning up the volume on the signal you want.
Good analogy. It helps overcome the probabilistic nature of quantum measurement sometimes.
Okay, so the theory is powerful, but then comes the reality check in the essay. What are the big practical roadblocks right now?
Well, as we touched on, current quantum computers are noisy. Decoherence is a huge issue. The quantum state losing its quantumness due to interaction with the environment. This leads to errors.
So the calculations might not be accurate enough.
That's a major concern, yeah. Then there's the limited number of qubits. We can't yet handle the billions of parameters of state-of-the-art AI models directly on a quantum chip.
We're talking maybe hundreds of qubits, not billions.
Exactly. And connecting the classical and quantum parts efficiently in these hybrid systems is also technically challenging. There's overhead involved.
So full quantum training for massive models is still a way off. Which brings us back to the hybrid systems being key for the near term.
Absolutely. The essay really emphasizes this. The workflow is classical computer does some setup, maybe pre-processes data.
Hands off the hard part, the gradient calculation, to the quantum chip.
Right. The quantum processor does its thing, calculates or estimates the gradients.
Then sends the results back
to the classical machine, which uses those gradients to update the AI model's parameters, and the cycle repeats.
Okay. And the essay mentions some of the companies building the hardware for this.
Yeah, it gives a quick rundown. IBM Quantum. Using superconducting qubits, they offer cloud access to their machines, like the Eagle processor with over 100 qubits.
Google too, right, with Sycamore.
Yes, Google Quantum AI, also superconducting qubits, known for some key research milestones, and Rigetti, another player in superconducting tech, focused on integrating quantum and classical systems.
So the hardware exists even if it's limited? What about the software to actually use it for this stuff?
Crucial point. The essay highlights key frameworks: Qiskit from IBM is very popular, integrates well with Python tools like NumPy and TensorFlow that AI researchers already use.
Makes it easier to adopt, I guess.
Definitely. Google has TensorFlow Quantum, specifically designed to bridge TensorFlow AI models with quantum circuits.
Okay.
And Penny Lane is another important one, open source, really focuses on these hybrid quantum classical models. And it can work with different hardware backends like IBM's or Google's and integrates with PyTorch too.
So the tools are being built, but the essay still flags major implementation hurdles. Can we recap those main challenges?
Sure. It really comes down to 1, quantum noise and decoherence messing with the accuracy.
Yeah.
2, not enough high-quality qubits to scale up to huge problems yet.
Scalability.
And 3, the sheer complexity of making these hybrid systems work smoothly together, getting data back and forth efficiently, synchronizing everything. It's non-trivial engineering.
Despite all that, the essay sees real potential. Where could quantum-accelerated backpropagation make a difference first?
Well, think about areas where training time is a major bottleneck right now. Medical image analysis, faster training, could mean quicker diagnosis of things like tumors.
That's compelling.
Or large language models. Imagine cutting down the weeks or months it takes to train the next GPT. That would accelerate AI development hugely.
Yeah, definitely.
Also, reinforcement learning, like for robots or game AI. Faster optimization could lead to much smarter, more capable agents developed more quickly.
And the essay looks beyond just AI research to other sectors.
Absolutely. Healthcare, for instance. Faster simulations for drug discovery, maybe improving things like protein folding predictions, think AlphaFold, but potentially faster training, optimizing clinical trials.
Huge impact there. What about finance?
Faster risk modeling, portfolio optimization, maybe quicker fraud detection, areas where complex calculations and speed are critical.
And cars, autonomous driving.
Yeah, optimizing real-time route planning. Faster processing of all that sensor data, cameras, LiDAR, radar, could lead to safer, quicker decisions for self-driving vehicles.
So the potential applications are broad if the tech matures. What's the long-term vision presented in the essay?
It paints a picture of a possible future where AI itself is co-designed with quantum hardware in mind. Maybe new types of hybrid AI architectures become standard.
A paradigm shift, almost.
Could be. It also raises the hope of tackling grand challenge problems currently beyond our reach, complex simulations in climate science, quantum chemistry, materials discovery, astrophysics.
Problems that classical computers just choke on.
Exactly. And accelerating the whole innovation cycle, because AI models underpinning scientific discovery could be developed much faster. Plus, maybe a path towards more energy-efficient computing in the long run.
Okay, but the essay is balanced. It asks, when does quantum actually make sense? It's not a magic bullet for everything.
No, definitely not. It compares quantum's potential advantages: speed for certain computations, maybe better handling of complex optimization against classical methods, which are still improving rapidly.
And classical is often good enough for many tasks, right?
Precisely. Plus, you have the current quantum hardware limits, the noise, the qubit counts, and the overhead of running these hybrid systems.
So the sweet spot.
The essay concludes it's likely going to be for those really large, really complex problems where classical methods truly struggle and where the speed-up offered by quantum provides a critical advantage. Niche, perhaps, but high-impact niches.
Right. Now, beyond the tech, the essay touches on ethics and society. What are the concerns there?
Important points, like potential inequality. Who gets access to this powerful quantum tech first? Could it widen the gap?
The quantum divide.
Yeah. There's also the risk of misuse surveillance, autonomous weapons development being accelerated, and data privacy if quantum allows much faster analysis of large data sets.
And broader societal effects. Jobs.
Potential disruption through even faster automation, for sure. And questions about ensuring fair access to these potentially transformative resources. We need to think about that now.
Absolutely. And what about sustainability? We know AI training uses tons of energy now. Does quantum help or hurt?
It's complicated. On one hand, if quantum calculations are fundamentally more efficient for certain tasks, it could reduce the energy needed per computation in the long run. Optimized hybrid systems might save energy. But current quantum computers themselves often require significant energy, especially for things like cryogenic cooling systems needed for superconducting qubits. And manufacturing the hardware has an environmental footprint too.
So it's not automatically greener?
Not necessarily, no. The essay suggests we need strategies like better cooling tech, using renewable energy sources for quantum data centers. It's an active area of research.
Okay, so looking ahead, the essay's final thoughts on the future of quantum accelerated backpropagation. What's next?
Continued progress on multiple fronts. Better quantum hardware, more qubits, less noise, better connectivity. More efficient quantum algorithms tailored for gradient calculation.
Refining those hybrid approaches.
Exactly, making the classical quantum integration smoother. Standardization, open source tools will help drive adoption. And adapting these techniques for specific types of AI problems where they offer the biggest benefit.
How might this integrate into the broader AI landscape eventually?
The essay envisions possibilities like quantum processors becoming specialized accelerators, maybe like GPUs are today, used just for the toughest training tasks. Automated systems might learn when to offload parts of a problem to a quantum computer. Maybe even quantum capabilities on edge devices someday, though that's further out.
Lots of challenges still, obviously.
Huge challenges, but the potential breakthroughs in the coming decades. The essay hints at things like accelerating progress towards artificial general intelligence, maybe enabling revolutionary scientific discoveries, making powerful AI more accessible, perhaps even new hardware paradigms beyond silicon, and hopefully more sustainable AI too.
Okay, let's try and wrap this up. What are the main takeaways from our deep dive into Jorgo Schneppeut's work today?
I think the key thing is that quantum-accelerated backpropagation, while still very much in the research phase, it represents a really intriguing pathway to push past the current bottlenecks in training large, complex AI models.
It leverages those unique quantum properties, superposition, entanglement, to potentially speed things up dramatically.
Right, but it's not magic.
Right.
There are serious hurdles, noise, qubit limits, the complexity of hybrid systems. It's early days.
So the potential is immense across many fields, science, medicine, finance, but realizing it depends heavily on continued R&D.
Absolutely. Progress in both the quantum hardware itself and the algorithms, the software that run on it, is essential.
Which leaves us with maybe a final thought for you, the listener. As this quantum technology continues to mature, how do you think it will fundamentally change AI research and how we use AI? What new things might become possible that we can't even really imagine right now?
It's a fascinating question to chew on. The landscape could look very different in 10 or 20 years.
Indeed. Well, this deep dive was based on the essay and insights from Jorgo Schneppeut. Thanks so much for joining us for this quantum deep dive.
Thanks for having me.